Okay, so the in the end of last lecture, I speeded up a bit, so I maybe just quickly recap. So I used the fundamental relation, which is basically a form of Young-Baxter equation. So this will be right, and so this is one equation, and if you want to imagine it a little bit better, you can think of this again. What is the gate now for us? The gate is basically, as I said, is 1 plus I tau times permutation. So you can think of this. You can think of this box again, just using just diagrams. You can think of this box as identity, which is this, right? I mean, let's say this would be the identity of a pair of qubits, right? I mean, it maps a pair of states to the same pair of states, right? And then there is I tau times a permutation. What is permutation? Permutation is a swap, right? So you can think of this like that, right? And what is this diagram? Again, there are maybe some arrows like this. So this diagram is basically it's just the R matrix, right? So it is just not to make it okay. It's basically the same object, right? Just tilted, right, for 45 degrees, and multiplied by the swap, right? And then again, I mean, you can just write this diagram are just a bunch of identities, right? For identifying diagrams, right? This is like polynomial diagram valued polynomial, right? If you want, and you just compare orders, right? Of everything. So what we have now is basically another. So I wanted to give you another two claims, right? Moreover, aside from my central claim, which basically establish integrability of the general kind of circuit which is formed out of the solution of the Young-Baxter equation, we have moreover two additional claims, right? So this is basically Young-Baxter equation, right? Implies two more things, right? One is that transfer matrix commutes with itself for different values of the spectral parameter. So this is for arbitrary pair of lambda and mu. And maybe I have to tell you another thing, right, which is useful. Once you try to prove this identity, you need a slightly different form of Young-Baxter equation, which is, so maybe we can call it this number 1. And then there is also a sideways Young-Baxter equation, which you might want to need, which I will call number 2. Too strong. Which is, you take this guy like this. This is lambda, this is mu, and this is lambda minus mu. This is mu, this is lambda. So basically, this is like I don't know I should probably use a slightly different symbol. This is let's say again flipped by 40. This is a R matrix which is read in this direction. So. Now this is U, but you see U always gets two indices from below, but here it gets from, sorry. make too much garbage. This is U, which gets two indices from a side. But anyway, so this is, I mean, it's not the main point, but just as a side remark that you could, I mean, you should use another form of Young-Baxter equation if you want to prove the involutivity of this transfer matrix, because then what you do, you see, you just write two transfer matrices, like two rows, right, which are formed out of these Lax operators. One has lambda plus, lambda minus, lambda plus, lambda minus. The other has mu plus, mu minus, mu plus, mu minus, and then you from a side you take a stack of two R matrices, right, or two whatever. I mean, these guys are unitary in this sideways direction, so which means this is lambda minus mu, and this is mu minus lambda. So this is identity, because these are negative to one another, or it's the other way around, lambda minus mu, and this is mu minus lambda. So this means you invent identity from a side, then you push one piece of identity through, right? Because when you push it through, you exchange spectral parameters. Now this is mu, this is lambda. And of course you do it, but spectral parameters are staggered, but it doesn't matter. The difference is constant, right? It's either lambda plus mu plus or lambda minus mu minus. The difference is the same. So you can just always push an R matrix from a side, which has a fixed difference of spectral parameters. You push it through. What you get in the end is the exchange of lambdas and mu's, which means you get a product T times lambda times T times U equal to T times U T times lambda. I mean, that's a very standard proof, of course, in integrability. So I mean, this is nothing particular for the circuits here, but I just remind, just for those who have never seen that, I give a quick reminder or intro. Anyway, so another kind of thing that it's useful to have in your pocket is explicit expression of the time evolution in terms of a transfer matrix. So this transfer matrix is in fact not an independent object. It's the same kind of family of operator-valued functions, which also allows you to compute the time evolution operator. So this is actually, well, this is number 2 and this is number 3. If the main thing, the commutativity of T with U was number 1. So this is a kind of nice formula, okay, which I will not even try to prove it for you, but I give it as an exercise. I mean, you really use just this identity, which we established very well, and it's just straightforward construction, right? You should, of course, use the fact that that R matrix is unitary, so you can easily compute the inverse. But you see, I mean, for those, again, who have enough experience in integrability, they should probably recognize here a sort of a logarithmic derivative, right? I mean, if tau becomes small, right, then this goes to a logarithmic derivative of transfer matrix around lambda equal to 0, right? Argument equal to 0. And that's exactly what people usually write as a Hamiltonian, right, as a logarithmic derivative of the transfer matrix at the special value of spectral parameter. Now here we are not after any Hamiltonians, we're actually after finite time evolution. But finite time evolution in this discrete time setting is just a kind of, rational function of the transfer matrix. Yeah? Of course, tau commutes with itself, so it doesn't matter which side I write this inverse on. Okay, so that's kind of useful, yeah, to have. Okay, so now, but what can we do with these objects? We can compute conserved charges, for example, local integrals of motion. So now it turns out that you should not, when you have finite tau, you should not differentiate with respect to lambda equal to 0, but you should differentiate with respect to lambda equal to plus or minus tau over 2, because imagine transfer matrix, I don't want to write it again. The transfer matrix was a staggered product of R matrices evaluated at lambda plus, lambda minus, meaning lambda minus tau over 2, lambda plus over tau over 2. So depending on whether you put lambda plus or minus tau over 2, you have every other Lax operator or every other R matrix will be evaluated at spectral parameter equals 0, which means it will be just a shift, right? Because R matrix, not the U, but the R matrix at lambda equal to 0 was just a permutation, right? Just a permutation. So that is, again, similar to, again, for people who did it before, they know what I'm talking about, but I don't want to waste too much more time. So, I mean, the argument is very similar than how to show locality, right? So this object, you know, when you take a finite order derivative of the logarithm of the transfer matrix, so let me write it as lambda qn with some index plus minus. So I will take the nth derivative of the logarithm of t of lambda, and evaluate it at lambda equals plus minus tau over 2. I will get the two families of objects which are local, can be written as qn plus minus pi 2x, pi minus 2x, sum over x. So these guys are translation invariant. They're translation invariant with periodicity of shifts of two sides, right? So they are translation invariant only up to a shift by two sides, not by one side, because of the staggered structure of the problem. So you can think of them as being sums of densities which are supported on n sides. Well, are there exactly n sides? I think the way I wrote it is n plus 1 side, so let me write it like that. So now this would be like let me write a bracket like this. So this will be an operator which is supported on n plus 1 sides. Yeah, so I think it's, sorry, I make a mess here. I think it's n plus 2. Because already for n equal to 1, the first derivative, you have three side densities. Only in the limit tau going to 0, they become a two-side Hamiltonians of XXZ model or XXX model. But for a finite tau, there are already corrections. So even for n equal to 1, so for the first guy, you will have three-side objects, right, on n plus 2 sides. Okay. Now the point is, yeah, these are local densities, and now these are kind of translation invariant. I mean, they're shifted around by shifting by two sides and summing over the shift. Okay, so now right. So I mean, there was yeah. There's often a discussion. What is an integrable model, right? What is the proper definition of an integrable model? So many people would actually think of. I mean, there are papers about this, right? And some papers claim that the most abstract definitions of integrability, because it's not so clear, right? I mean, what Young-Baxter equation means and how it is hidden behind the given model. Sometimes it's more straightforward, sometimes it's less. So some people would claim that the existence of local charges is kind of the most kind of robust definition of integrability, and here they are, right? I mean, this is a tower of infinitely many conserved charges for a large enough system. For infinite system, there are infinitely many. For system of size L, there are of the order of L of them. There are L over 2 local guys, right, of size of type plus, and there are L over 2 guys of type minus, and so on and so forth. So now the question is, of course, is this always possible? And I will not have time to talk about this in my lectures, but I think it is not always possible to write local charges. I mean, this kind of magic that this logarithmic derivative become local, I mean, it's only possible when you have a particular point at which R matrix reduces to a permutation, which might not be always the case. I mean, there might be integral models for which this is not the case. So, I mean, it's a kind of subtle point of discussion. But anyway, I mean, here they are. So this is the usual story. Okay, so now. Right, so now let me go back let me try to generalize to XXZ.
Can you also maybe comment, because in the previous case you had like a gate U, and then the permutation times R matrix was a gate.
Yes.
Are you going to think also about this higher charge
No, because they are not unitary. I mean, they are Hermitian, right? They are not unitary, so I don't think we can interpret them as gates.
Automatically enter because they commute.
What do you mean they enter? I mean, they commute.
If you build a circuit out of
They automatically commute with the one layer of the circuit, right? Right. So that's what you have. I mean, so that's why they are conserved, right? They commute with one layer of the circuit. That is also with any number of layers. But yeah, so they are. Okay, so now there is, I mean, for the end of this part, because I should probably quickly close this part and go to something else, but for the end of this part, which I was thinking this would be like the first lecture, it's already extending into the second one, but I wanted to discuss some physics, right? I mean, these models actually, they may look a bit abstract, I mean, or technical, or whatever you want to call it, but I think there is lots of interesting physics hidden in these models. In particular, you can first of all generalize these circuits to what you may think of XXZ circuit, or you can just go, this was a 6-vertex model, right? But this was a 6-vertex model at the trigonometric point. Now you can extend it. You just go to an arbitrary 6-vertex, unitary 6-vertex, right? So you can just say, okay, let me take U of lambda, again, the same form, AB, BA, a symmetric 6-vertex weight matrix, but then you take A as sine eta divided by sine lambda plus eta, and B sine lambda divided by sine lambda plus eta. I mean, this is now, you introduce an additional parameter, eta, which is the so-called deformation parameter. Sometimes people call a Q parameter, which is, I mean, eta is related to Q by Q equal to e to the I eta, right? So this is the so-called quantum parameter, and but I will prefer now to use the eta parameter. So we have two parameters. One is a spectral parameter, the other is a quantum parameter. And depending on the real or imaginary value of these two parameters, this matrix can be made real, unitary, right? I mean, we already have seen some manifestation of that, but now this was for Q equal to 1. But for arbitrary Q, we have at least two cases in which this becomes unitary, two regimes. Let's call it unitary, two unitary regimes. One is when you have imaginary lambda and real eta. This would be what I would consider easy plane XXZ circuit. And when lambda is real, so either one of, what one needs to have is that one is real and the other imaginary, right? Otherwise, the matrix is not real. This would be easy plane. Sorry, this would be easy axis. XXZ circuit. Now again, for the experts, this reduces to XXZ spin chain, right? In the limit, in the Trotter limit. Why in this case would be lambda going to 0, and also yeah. For example, this could be written as maybe I could just continue here. This could be written as e to the I j sigma x plus sigma y plus j prime sigma z, okay? So, this is like an XXZ Hamiltonian density, right? So this is J and J prime, and what people would usually denote as anisotropy would be a ratio J prime over J, okay? Now, what I want to warn you, this model is a bit more interesting than just the limit of lambda or tau to 0 of XXZ, because, for finite time step, the anisotropy is not simply J prime over J, right? If you, for example, write this phase diagram like that, if you draw this diagram like J prime, then obviously these two parameters are kind of, they're trigonometric, so they go up to from 0 to multiples of pi. Let's say pi over 2 is some fundamental domain, and then everything repeats, right, periodically. But you see, I mean, there is this kind of nice structure that, I have no time to go into detail, but this regime, which I call number 1 regime, easy plane regime, this corresponds to that region. That easy axis regime corresponds to that region, and then there is this, which is isotropic, right? Which is isotropic, meaning that it has a SU2 symmetry. So that's actually what we discussed earlier, right? This is the isotropic XXX case, XXX circuit. And people have done a lot of numerical simulations of transport properties, spin transport properties of this model. That actually, these models are most interesting because they show very rich transport behavior depending on the parameters. For example, they show phase transition, a kind of quantum phase transition at high temperature or at infinite temperature, if you want, between ballistic and diffusive or insulating transport via super diffusive transport. So this is, if you look at dynamical exponent of, you're computing some correlation functions. For example, you compute some spin-spin correlation function, right? C of xt, which is sigma z of so at position x at time t, sigma z at position 0, right? And then you look at how this correlation function decays at x equal to 0. That's autocorrelation function of spin. Then this defines dynamical exponent. Let's call it z. And z equal to is a signature of spin diffusion, which people were talking about or discussing since, I don't know, many decades ago, right? So this is one of the big questions, how to find, if one is able to find spin diffusion in spin chain models, in spin lattice models. So this is equal to, right? Z equal 1 would be equivalent to ballistic transport, ballistic spin transport. And z equal to 3 over 2, which is in between, would be a kind of a super diffusion. And in this model, what we have is here z equal to, so z1 is ballistic, so z equal to 1. Here it is equal to, and on this line, we have z equal to 3 over 2. And not only that, we have features of spin-spin correlation functions. For example, not only that this dynamical exponent gets this value 3 over 2, but this is 3 over 2 is basically a feature which is characteristic of Kardar-Parisi-Jeank universality. There are basically two known universality classes. I mean, you know about equilibrium stat mech, right? There is a lot of universality there. I mean, there is a good discussion of phase transitions and universality classes. In non-equilibrium physics, this is much less developed. It's much less clear. And there are two kind of, essentially basically two kind of really well-known universality classes of non-equilibrium behavior. One is Kardar-Parisi-Jeank, KPZ, and the other is Edwards-Wilkinson, or diffusive universality class, which are characterizing basically transport which is either of diffusive type or of super diffusive type. And in this problem, we find KPZ scaling, even though, I mean, if you want to discuss universality, one has to be careful, and I would need 1 or 2 more lectures for that, but which I don't want to go into now. The question is whether we have really KPZ universality in this spin transport, or we have just some sort of scaling, and we are still lacking some other elements of universality. It's the latter, but as I say, I will not go into that deeper unless someone wants to ask the question. Yeah, the point of this conclusion is that this story is on physics, in terms of physics, is extremely interesting. Yeah, and it's very nice that we have a kind of class of simple toyish quantum systems, quantum circuits, which kind of are simplest toy models of this type of interesting physics. I mean, that actually, people have run the quantum simulations on quantum computers. Google have 2 papers on this model running simulations of transport or, showing beta ansatz or integrability of this type of circuits and so on.
Can I ask a question? So the non-equilibrium aspect relates to the fact that you switch, that you have sort of discrete evolution and you switch?
No. Well, it has to do with the fact that you're doing real-time evolution, yeah. Now, the fact that you are switching, well, you may say, okay, yeah, it's a driven system, right? I mean, that's my question. I understand. I mean, that's a kind of just arguing, okay, since it's a driven system, the energy will not be conserved. But it's a generic integrable theory with infinite tower of conserved quantities. So there is a fake Hamiltonian which is conserved. There is a Q1 plus minus, or the difference in so the Q1 plus minus, the sum is what you may call a Floquet Hamiltonian. The difference is what you may call a kind of heat current, right? So these are the charges which are there and which are as honest as any charges of any honest integrable field theory or integrable lattice model. But the energy just so happens that the Hamiltonian is not none of these charges generates time evolution, right? There is a separate beast which generates time evolution, and which is only there for discrete time. So that's all. Yeah. Yeah.
Do you also do some averaging or some randomness in this term?
No, that's a cute part. Yes, we don't need any randomness. We still see KPZ. Actually, this is one of the main. I mean, if you ask me what is the main scientific challenge for the next decade for me, I mean, it's just to understand why KPZ happens here. People are still. These people are still puzzled, right? I mean, there is this. I've just been at the mathematical physics workshop somewhere in Bavarian Alps, where mathematical physicists like Alexei Borodin, Ivan Korvin, this type of people who solve, integrable models, in rigorous sense, and they find it extremely puzzling, right? Why this happens here, right? I mean, they are working with KPZ universality, every day, right? But in models like stochastic exclusion processes, like ASEP, things like that, where that is completely normal, right? This was like almost a definition of KPZ. But these models are models which are built on randomness, right? They are random models. They are stochastic models. Now, these models have no randomness whatsoever. I mean, they are like deterministic models. Yeah, quantum deterministic models. We can go to classical deterministic integrable models, the same physics. So you don't need, this is one of the things that I find scientifically the most kind of interesting. I mean, how can you explain statistical physics without intrinsic randomness, right? Randomness comes from somewhere. Well, in chaotic systems, we believe that randomness is produced dynamically, right, by the mechanism of stretching and folding, right? But in integrable systems, there is not such a mechanism. Yeah.
But that's also why I was very surprised to see, because it's integrable.
Exactly. So when you have integrability plus thermodynamic limit, you can still have interesting physics which resembles randomness. Yeah.
Maybe it is important that it's driven in some sense.
No, because the same physics applies to continuous Heisenberg. That's how it was actually discovered. We looked first at the continuous Heisenberg model, just throttle limit, doing honest DMRG. Then we said, okay, let's speed up our simulations. We don't have to do throttle limit in the DMRG. Let's just do finite time steps, the same physics, and you can go up to 20 times larger times, right? Because you don't have to do the throttle limit. But okay, that's okay. That's as much as I wanted to say so far. So, any other question? Because it's a good time to take questions now. Yeah.
Can you briefly explain what does the term easy phase and easy plane and easy axis mean?
Yeah. Okay. So that's as you in the usual Heisenberg model, this would be like these are the two couplings, right? And if the coupling along ZZ is stronger than XY plane, then this is closer to Ising model, right? Sometimes people call it Ising-like or Ising type phase, right? I call it easy axis case, okay? Because now the coupling is along the Z axis, right? If J is less than J prime, if J is larger than J prime, before J prime was larger than J, now if XY coupling is larger than ZZ coupling, then people call it XY-like phase or easy plane phase, because the interaction is in plane. It's a jargon from magnetism. Okay, any more question? Otherwise, I will change gears now, and I will just go to what I would call lecture 2. Still part 1, so still part 1, lecture 2. I make so much chalk. Anyway, so now I will discuss slightly different paradigm. I will discuss an open system. Actually, there was some question in the last talks of Julian, I think, about open. I mean, like observing a black hole or something. I mean, I will try now to ask a related question now in general many-body spin chain context, right? So let's say take our spin chain and observe it from the outside. So let's open it to the outside. I'll take what I call boundary-driven dissipative circuits. I mean, I could speak about boundary-driven spin chains in the Hamiltonian setting, but since we are doing everything for the circuits in my lecture course, I will just stick to the circuit part, so I will consider boundary-driven dissipative circuits. So it's actually, again, a model which can be easily simulated in a lab. Again, what's happened now? This guy died. Okay, let's see. No, it didn't die. It just didn't sense my, somehow maybe it's, no, it's okay. It still has 30%. I don't know what happened, but it's just sensitivity of screen is somehow. Okay, so yeah, so what we are doing now is basically we are taking a chain of qubits. Now I can imagine like a little spins. And then I will just, couple them to the outside world. This is a 1D system, right? So its boundary is just two sides, the first and the last side. So let's just couple it at the boundaries. That makes sense, right? If we are not trying to mess up with the bulk. Now, we can go back to the problem of noise, right? I mean, the question is, what is the minimal model of noise? To my kind of understanding, the minimal model of noise would be like, take a bulky system, and then you couple it system in some bulk, right? I mean, defined with respect to some bulk. So bulk has some boundary, so it only sees the outside world through the boundary. So in 1D, the boundary is just these two sides. So now I will just take coupling here, right? So now let's put these dots as a kind of dissipative coupling. So the first and the last bit are this qubit or qdit. Now in this case, I will only consider qubits as usual. But only the first and the last is coupled to the boundary, and the rest is again completely conservative, completely uncapped, completely unitary. I mean, it's evolved with respect to unitary gates. As I say again, this is a kind of a model which, well, there are three kind of things I can say to motivate this type of model. First, okay, this is not the usual model that people who do many-body open quantum systems do. People usually look at Limblad or whatever processes in the bulk as well, because that's also natural. But you might want to discard the bulk dissipative processes and only look at the boundary. The second motivation why maybe the better motivation why I like to think of these models is that in these ways I get some sort of minimal problem which teaches me something new about the bulk unitary bulk physics. So since the unitary part of the bulk part of the system is still unitary, what I will learn from this will still tell me something about the physics of the unitary dynamics. Yeah? These are just unitary dynamics with dissipative boundary conditions, if you want. And the third point why I could be motivated is because, again, I will cite again group of Google. These guys have actually implemented this on their Sycamore processor. They have actually a paper, again, in Science in 24, where they have simulated exactly this type of paradigm. So they look at the boundary noise. They basically reset qubits. They basically stochastically reset qubits at the boundary according to their desire. For example, this one to point upwards, and this one to point downwards. And then they repeat. So they do exactly the protocol I will be discussing now. Okay, but Okay, right, so what is the model? Now I make a model. Of course, we need a mathematical model because we can only solve simple mathematical models. So let's take a model of this time evolution. Now this is an open system dynamics. So the system is described by a density matrix. Now the density matrix, of course, again, is a matrix, is an operator over HL, right? Is an element of space of linear operators. It's a positive, not only that, it's a positive and self-adjoint. It's positive Hermitian, right? All eigenvalues larger or equal 0, and the sum of eigenvalues equal 1. And that operator has the following dynamics, which you can think of as quantum Markov chain. So this is like a quantum Markov chain dynamics. I mean, there are many buzzwords, right? Some people think of this as called this quantum Markov chain. Some people call this completely positive maps. So the point is this M is a machine which acts on a density matrix and produces another density matrix after the next time step, right? By iterating, by applying time evolution by 1 unit of time. Let's say what we will, I mean, let me be very specific. What I will do is I will split this M. Now this M is, again, is just what some people will call a super operator. So it acts, it's what Julian was talking about when he was introducing operator spreading, right? I mean, there is Liouvillean, right, is an example. I mean, his Liouvillean is an example of super operator, right? It acts on a space of operators. Now our density matrix is also a representative of space of operators. So now this guy, we can again split into odd and even part. And even part acting on the row is a linear map which conjugates a density matrix in Schrödinger picture with even part of time evolution, right? But on top of that, it produces some dissipation, and dissipation is generically parameterized what people call it Krauss operators. So let's define Krauss operator on the right first. I will make a picture later, but this will be Krauss operator localized on the right end of the chain. So that's why I will put superscript R, and then some index mu, which in my case will run over 2 values, 1 and 2. And similar for the other part. So this is the odd part. And okay, so I forgot to put a adjoint here, right? This has to be Hermitian adjoint. Okay, so these are Krauss operators. Krauss. So Krauss has, you know, it's one kind of generic way of writing completely positive dynamics. So which means you map rho into a sum of k rho k dagger. This is a completely positive map. It's a general completely positive map, right, which preserves positivity and trace of the density matrix. It also preserves it's also preserved. Especially nice Krauss maps are such for which, well, first this identity has to be fulfilled, right? I mean, this is guaranteeing trace preservation, which I forgot to say. So this basically means trace preservation. Okay, so right. So I mean, and okay, I will try to be as non-technical as possible. So I will just specify the problem here, and the problem is, of course, already known problem. So it's U even will be U12, U34, up to U L minus 2, L minus 1, and now I will assume that L is odd. It will be convenient to assume that L to be odd. And then at the last site, I will put some magnetic field on the L side. Right? This will be the unitary part. And the odd version of the unitary part of the odd piece will be starting with magnetic field on the first site. Let's call it B left. Now don't confuse L with a number of sides. Yeah, I'm sorry for that. L here is just a magnetic field at the left. U 2, 3, U 4, 5, up to U L minus 1 L. And again, I will make a picture to make this more clear, but then let me just continue with the Krauss operators. So these are the simplest kind of Krauss operators which implement this kind of amplitude polarizing channel. So there are two Krauss operators for each boundary. This L means left. So this is a diagonal Krauss operator, which is there just in order to fulfill this identity. But this one, the second one, is crucial. This is some square root of some dissipation times lambda sigma 1 plus. So this is a spin raising operator, right? So this will be just, this could be, I mean, for people who have never seen this, but they have maybe seen the Lindblad equation, right? Lindblad equation is a continuous time version of the Krauss. And this is just like a jump operator, right? This is like a Lindblad jump operator, which will produce a process in which spin will jump from spin down to spin up, like stochastically, right? I mean, this is a stochastic process which will allow for, where do I have a picture? I have made a picture. So this will be a process which will allow to flip this guy stochastically, right? Because intuitively, you can imagine you have a magnetic reservoir on the left and on the right, which is kind of stochastically coupled to the rest of the system. So, I mean, this is just an idea of a reservoir, right? I mean, you have a reservoir which allows you that the first spin kind of flips stochastically because it's coupled to a thermodynamic reservoir. And then the other one, the right end, is similar. I just need to change some signs. Yeah, I really don't like this fact that I use letter L for system size and for, but I have to keep it now because it will be too messy to change, sorry. So here I just change signs, minus, plus, plus, minus, and also this guy is flipping downwards. Sorry, this is the last one which flips downwards, okay? So these are the two kind of canonical spin raising lowering processes. And what are we doing now? I mean, what is the picture which, what is the diagrammatic picture which represents this kind of process? Well, we can think of it like this. We can define a density, well, we can define, well, first of all, we should think of density matrix again as a vector, right? As a vectorized object. So we do the so-called vectorization. So this has different names. I mean, some people call it super operator picture. Some people call it thermal field double picture. It's the same thing, right? It just when you have an operator object, object which is an operator, you can just embed it in the linear space, a vector space, and you treat it as a vector, and then you can construct operators which act on this as vectors, right? So, for example, which means our density matrix will be now written as density matrix, which is canonically written as in a bracket notation like this, will get mapped to a structure like this, which means you just take, I mean, this is a kind of, if you want linear or bilinear, yeah, it's a linear map, which is antilinear in the second argument, but once you fix the basis, this doesn't matter. And this I will write as a vector, which I denote simply as a bracket row. Okay, now what the time evolution does. Now time evolution, basically, I will now depict as doubled box, right? Now this will be tau, and behind there will be minus tau, because it's inverse time, right? I mean, this is u dagger, right? This is u, and behind it's u dagger. And this applies, the first legs go in, the second legs go, the legs behind go down, go reverse direction, right? I mean, I will not, of course, bother you with these arrows and with this structure anymore, but I just want to define it precisely, right? So it's like forward, backward, right? If you want, it's like a forward, backward, or Keldysh contour picture, right? You have forward evolution, behind you have backward evolution, right? You have one piece of this forward, backward, right? Which in the vectorized notation would be just one box. And now in our usual sense, right? And this will be applied to a density matrix. But in our usual sense, density matrix will be a box. And here will be tau, and here will be minus tau. And now what people sometimes call is a folding notation, where you put this guy, you just make it out this from the paper, and then just fold this guy behind, right? And then you get this picture, right? So this box is folded behind, so it's this guy here, right? And now, out of this box, which you call a density operator, becomes a vector, which is vectorized density operator, right? Because it has only upper legs, no in and out legs. Okay, and now what is the M now? What is the time evolution operator? The time evolution operator has now this nice representation, right? It has the lower part. Okay, I will just for the time being still write these double boxes just to make. And now, okay. These are the two Krauss operators behind and in front, right? And now these two Krauss operators are coupled sideways, and this is my index mu. That index mu, which have to be summed over, right? Where was it? It was here, right? There is an extra index that Krauss operators depend on, right? Krauss operators are matrices or QDID, but then they depend on this extra index, right? So there are like three leg symbols, row, column, and this mu index, and this mu index have to be summed over. So it's only summed over these tensors, right? So once you do this vectorized picture, then all are just black box, right? They're just different black boxes. These are unitary boxes. They implement unitary dynamics in Heisenberg picture or in Schrödinger picture, but in operator space. And these guys are non-unitary objects. They are completely positive maps, but of a single qubit. Now there is no periodic boundary conditions anymore. Everything is nicely open. So now this would be the first step, which I will call M odd, and now M even. I call it M even, right? This guy on the right, yes. And now I will write it, the second guy like this. Because that will be our diagram or cartoon picture for the many-body completely positive map, which we are now after to analyze. Yeah. So any question? Everything clear so far? I mean, that now I understand it's a bit of maybe for more than previously of you. It's a bit of there are some new concepts here. So maybe if there's any question, let's clarify before. Okay, let me just be precise on what do we mean. Yeah.
Maybe I can just make the comment.
Yeah, sure.
To everyone, but this row at the right is the exact same thing that I denoted with the round bracket, just to make the comment.
Okay, good. Yes, it's good to connect notations, yeah, between different lectures.
No, I mean, use your notation.
Yeah, no, I mean, I will not use it often, so it doesn't matter. But I will again, most of the time, try to use diagrams. But okay. Right. So now I should remind you, of course, that this circle, okay, contains slightly more than just Krauss operators. It also contains magnetic field. So that means that when I will apply this circuit on the row of a single qubit, then what I mean is again mu going from 1 to 2. I mean this box, which was rho unvectorized, and then there is magnetic field e to the minus IB sigma z, e to the plus IB sigma z, and then there is a cross k mu, and here it's a joint cross. I mean, I don't want to write inside the box because it's not enough space, so I'll write aside, right? You see, this has to be, this is for time evolution, this is backwards, so it has to be Hermitian conjugated, right? So that's why there is no minus here, and that's why there is the dagger here. And now again, by you doing folding, I would just do like that, and then everything besides the row would be this circle, right? So the circle will be the map that acts on that. Okay, now fine. I mean, I'll introduce the language, a slightly novel language. But the reason why I want to do that is because there is a very kind of nice way of understanding fixed points of these dynamics in terms of integrability. So now what you might be interested in, of course, you might be interested in full dynamical evolutions of this quantum Markov chain, right? I mean, you want to be in particular interested also not only in to what state it converges, but also how fast it converges, meaning that there is a question of the gap, of how the gap scales, right? I mean, what is the time scale of the convergence? These are all interesting questions, but the first and the most important question is, of course, the structure of the steady state. Because this model is now not an equilibrium problem, right? This model is driven. It's driven not only in the sense that it's time periodic, that the gates are switched on and off constantly. It's driven also because the left and the right boundary are trying to run the current through the system, right? So it's really driven. I mean, it's driven, in a strongly non-equilibrium sense. So it has a state which is not a flat state, which is not a infinite temperature or Gibbs density matrix, but it's a non-trivial state with a current. And it's very interesting and very important to find this state and to learn some physics out of this state. And that's the purpose of the rest of this lecture. So I'm not sure how much time I can still afford. It's, yeah, I have like 25-ish minutes more, right? Which hopefully will be enough just to tell you a little bit on the structure of this state, because that's probably needed in order to have some sort of closure for this lecture. Okay, so now, yeah, what I will try to do now is I'll try to find a fixed point, right? Fixed point of M, which is the so-called non-equilibrium steady state. And what is a fixed point? Well, a fixed point means a state which I will call rho infinity, which is preserved under this map. So this state should be reached after a very long time, after you do simple iterations, right? This is the state which you will have to find. And this you can also factorize in pair of states, which I will call rho infinity prime, which will be given by applying M even on the rho infinity. And then rho infinity will have to be without prime will have to be returned by applying MO on rho infinity prime. Okay, so these two equations are equivalent. Just I will just use the fact that I can split this in two pieces, and after applying first piece on rho infinity, I get rho infinity prime by definition of rho infinity prime. Then I should get rho infinity back. So. And then there are a couple of things I can observe. I mean, I have to use at least half of the next lecture to close this, because I really want to do that. But before, as I said, I mean, just to tease you enough, I have to give you a little bit on the structure of this state and maybe some hint how it's connected to integrability. So, okay, so now two things. These are just claims, which I will probably have to prove tomorrow, but still, it's maybe good to give you the claims. The claims are the following. This state can be nicely factorized in a way which reminds of a kind of, density matrix is a probability, right? And probabilities in quantum mechanics are modular square of amplitudes, right? So this is a kind of operatorial amplitude. So let me call it as amplitude operator. And in order to normalize it to have trace 1, I will introduce a non-equilibrium partition function, Z. So this is just 1. So now omega will be what I call amplitude operator. So we are trying to split the problem into simpler problem, right? We will try to split the problem now for the amplitude operator. If there is such a factorization, which is kind of nice and clean, then maybe problem or conditions for the omega could be simpler than for the full row. And that's actually what happens. So it happens that omega can be written as a transfer matrix. So now we are turning back to integrability. So the point is, and this is something that I have to prove tomorrow, but at least I want to state the solution. I will write now a string of Lax operators. Now they are no longer R's, but they are honest Lax operators, because now we are not looking at fundamental representation anymore, but I will explain what we are doing. So auxiliary space is now something else. This is auxiliary, comma 1, lambda, comma s. I don't know why I did. I should probably, it would be better to put the other way, like that. 2a, here I will take lambda minus tau, comma s. Remember, lambda is odd, so now this has to be again lambda minus tau, comma s, lambda, comma s, and then closed in the same state. And then what I have now is a Lax operator, L lambda s, which is a 2 by 2 matrix with elements. Now I'm just assuming XXX case. That is u of tau is just 1 plus I tau permutation divided by 1 plus I tau. Everything straightforwardly generalizes for XXZ, but to make life simple, I'll do just the XXX case. In the XXX case, I have a very simple form of the Lax operator, which you can read from any textbook in integrability, like Faddeev review paper or Korepin's book or whatever. It's always there, right? This is a very standard thing. Now, usually, again, you are thinking of S to be in fundamental representation. So this is a 2 by 2 matrix of usually 2 by 2 matrices. But in our case, these guys are not 2 by 2, but they are something else. And they depend on some parameter which I call small s, which is this little small s here, which is what I call a representation parameter. And this guy is the highest weight state. This is the highest weight state of this representation. So this is basically a spin S representation, spin S. So these guys, S plus, minus, and SZ, form a spin S representation, irrep, of SU2. Okay, nothing unusual, except that this S is a complex number, which is not real. Not even half integer, not even real. It's a complex number. So we are looking for non-compact representations of SU2. I mean, we have to use non-compact representation of SU2, so a complex spin. I mean, I know that in high energy physics, people have played with that for many years, and also these concepts are used in contexts which I cannot really appreciate. But here in this type of kind of condensed matter, like physics, I mean, this was a kind of surprise that you need complex or non-compact spin representations of the symmetry of the problem. So, but again, I mean, now you see, I should close, yeah, and I will close. But I just want to give you a kind of a flavor of how one should now continue to prove that, right? I mean, the idea is, okay, now we'll write a tensor diagram for omega dagger. It will just 2 stacks of omega. One will be conjugate with respect to another. And then we'll apply M on it, right? We'll apply M on it, or we can fold it or unfold it as we like. But we see, I mean, then we'll again use this fundamental Young-Baxter relation. But now these diamond shapes will have the auxiliary space, which will be non-compact spin. We'll be carrying non-compact spin. So it will be infinity dimensional, not 2-dimensional. So this object is also a kind of, I mean, people could call it a matrix product state, but the bond dimension, the auxiliary space is non-compact, it has infinite dimensionality. But you start from highest weight state and you end up with highest weight state, which means you can only climb up to, let's say, L over 2 sides in this representation ladder, and then you have to go back, right? So you only need L over 2 states in this auxiliary space for any representing a state in any finite system. Okay, so now I think I will close here, so I'll spend maybe another 20, 30 minutes of the next lecture to explain how to prove that and what is the physics of it. But here I have to close for today. Thank you.
We still have time for questions.